We're going to conclude Unit 9 with a study of some topics in probability. Okay, so we'll find the probabilities of events, and we'll find the probabilities of certain types of special events, mutually exclusive, independent events, as well as what's known as the probability of the complement of an event. So just some terminology, which is really important, so you know what you're referring to. Any happening, anything that goes on for which you have an uncertain result or an uncertain outcome, we can consider an experiment. Flipping a coin can be considered an experiment because when you flip it, you don't know whether it's going to land heads or tails. Okay? The possible results of that experiment, in the case of the coin toss, the possible results are the outcomes. So the outcome could be heads or tails in the case of flipping a coin. We're not going to count if it lands on the edge. Okay, the set of all of the possible outcomes is known as the sample space of the experiment. So in the case of the coin toss, the sample space would be heads or tails. It's one or the other, and that's it. That's everything it could come out to be. And any subcollection of a sample space is known as an event. Okay, so if you flip a coin that lands on heads, you have a head event. Okay, the example here, a six-sided dice is tossed. The sample space, what could it possibly happen if you toss a die? Well, it can come out in 1, 2, 3, 4, 5, or 6. Those are the only 6 possibilities. That represents your sample space. And in this example, each of those outcomes is equally likely. It's just as likely to toss a 6 as it is to toss a 1. So let's identify the sample space for each of these things. We already talked about a coin being tossed. The sample space here would be sample space is equal to heads or tails. If we're tossing 2 coins, then we add a little bit of complexity. So our sample space is going to be, well, we could toss the first one and get a head, and get the second one and get another heads. Or we could toss the first one and get a heads and then get a tail. Or we can get a tail and then a tail, or a tail and then a head. And I think those would represent, those 4 outcomes represent the entire sample space. There's no other way to combine it. Okay, now if we're talking about 3 coins, it's going to get a little bit more difficult in that we have more possible outcomes, but let's just try to organize it. So I'm going to say our sample space is going to be, well, we'll start with the heads. Heads, heads, heads. It could be heads, heads, tails. It could be heads, tails, tails. Okay. We could also have it starting with a tail and be tails, heads, heads, tails, heads, tails, 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 heads. Am I missing any? 1, 2, 3, 4, 5, 6. Definitely missing some. I could have tails, 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 and tails, tails, heads, tails, heads, tails. I think there's more. Stolen heads, 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 tails, heads, tails, 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 tails. So what do you have? 1, 2, 3, 4, 5, 6, 7 possible outcomes. I'm thinking there should be 8 for some reason. Oh, I see what we missed. We could start with a head, get a tail, and then get another head. And I believe that that represents all of the possible outcomes for the flipping of 3 coins. So when we're calculating probabilities of events, what we're looking to do, and you could read through this, but really what we're looking to do is determine how many possible outcomes we have, okay? And that would be the number of elements in the sample space. And that's going to become the denominator of our fraction. The numerator is going to be the number of desired, I'm going to call them desired. By desired, I don't necessarily mean that the outcome is good. Okay, you could be playing Russian roulette and getting a bullet in the chamber is not good. but that could be in an outcome. You want the probability of there being a bullet in the chamber. The what I mean by desired is that it's the outcome of interest. So if I'm rolling a die, for example, and I'm interested in coming up with 3, if it's a 6-sided die and there's possibly 6 outcomes, I'm interested in getting a 3. That's one of the 6 possible outcomes, so that would be a probability of 1/6. Okay. Okay. Probabilities must be between 0 and 1. Okay. That's just by definition, that's how we do probability. And if you have a probability of an event that comes out to be 0, that event is known as impossible. It can't happen. Okay, it has a 0 probability. Whereas if the probability is 1, then it's a certainty. It's a certain event. Okay, so let's take a look at this couple of examples here. We have 2 coins that are being tossed, and we're interested in the probability that both lands heads up. Well, we know that our sample space is going to be heads, heads, right? Heads, tails, tails, heads, or tails, tails. Okay, so we have 4 possible outcomes in our sample space. That's going to be the denominator. And our numerator, we're interested in, they're both landing heads up. Well, guess what? There's only one outcome that has both of them being heads. So there's going to be one outcome out of 4. Our probability is 1/4 or 0.25. Okay, a card is drawn from a standard deck of playing cards. How many cards are in a standard deck? 52. Okay, what is the probability that there's an ace? Okay, so well, we have 52 possible outcomes, and how many aces are in the deck? Well, there are 4, one for each suit in the deck. So 4 out of 52 we can reduce to 1 out of 13. So our probability of selecting an ace from the deck of playing cards is 1 out of 13. Okay, so 12-sided dice can be constructed. Let's say we have dice that have the numbers 1, 2, 3, 4, 5, and 6, and then again another 1, 2, 3, 4, 5, and 6. So there's 12 faces. Each individual number appears twice on those die. We want to prove that the probability of a number coming up is the same as is on a regular die. So let's just say we have a 6-sided die. Okay, the probability of any given number, okay, I'm going to call it probability of a number appearing, is going to be 1 out of 6. Okay, we're interested in one number, and there are 6 possibilities. Well, if we go with the 12-sided die, the probability of a number here, the numbers all appear twice, but there are 12 choices. Okay, 12 possibilities. So that reduces to 1/6, and you can see the probabilities are identical. Okay, so let's talk about winning the lottery. And the Arizona lottery, there are numbers from 1 to 41, and you pick 6. Okay, so we want to know what the probability of winning is. Well, this gets back, we need to figure out how many ways are there of picking 6 numbers, a set of 6 numbers out of these 41 possible options. Okay, and it really doesn't matter if you pick the numbers in a different order. As long as you get all 6 numbers, you win the lottery. Okay, so what we're really dealing with here is a combination problem. Okay, so our sample space, I'm going to call it NS, okay, N of S, is going to be equal to 41C6, 6 numbers selected from a total of 41 in this group. All right, so it's going to be 41 factorial. Well, let's take the shortcut. 6 factors: 41, 40, 39, 38, 37, 36. And you can do this on the calculator, of course. Divided by 6 factors, 6 times 5 times 4 times 3 times 2. Okay, and if you go ahead and do that, simplify it or work it on the calculator, you should get 4,496,388. Okay. Now, we're interested, that's our sample space. That is the denominator of our fraction. Okay, so it's going to be down here. Okay, we're going to call this the probability of winning the lottery. Okay, and we are selecting one group of 6 numbers. Okay, so that our chances are 1 out of almost 4.5 million. Okay. And we'll continue in the next video with some additional types of events.